Hello, and welcome to this introduction to scanning electron microscopy. Your presenters will be me, Soren, and Nicholas. To really understand scanning electron microscopy, we maybe have to define what is microscopy. If you look it up, you'll see that it's a noun that describes the use of a microscope. But what is a microscope then? A microscope is an optical instrument having a magnifying lens or a combination of lenses for inspecting objects too small to be seen or too small to be seen distinctly and in detail by the unaided eye. Normally, we distinguish between two main types of microscopes. There is the optical/light microscope, which is the one we know from middle school. This type of microscope existed for more than 1,000 years. It uses light as the source, and it has a complex system of mirrors and lenses to magnify objects up to 1,000 times. Then we also have the scanning electron microscope, the SEM. The early models date back to 1930s, and at that time the magnification was not significantly better than of optical light microscopes. As the name indicates, the scanning electron microscope uses electrons as the source. It consists of a complex system of lenses and coils, and it also uses vacuum to obtain the images. This will be explained later in the presentation. With the scanning electron microscope, you can reach up to 10 million times magnification, which is 10,000 times better than the magnification of an optical microscope.
Here are some key applications of SEM. First, surface topography and morphology. Next, crystalline structure and orientation of material. In overall, SEM is a qualitative analysis of materials. Here are some photos of what SEM can produce as images. The one on the top shows surface topography. The one below shows how crystalline the material actually is.
Now we have established where the primary electrons come from. Let's take a look at what happens when they interact with the sample.
This is a simple schematic of how SEM looks like. First, we have the source, also known as SEM column, the detector, and the sample. Next, we will discuss on the components of SEM column. The SEM column consists of 6 main components. First, the electron gun, which is the source of electron beam, and electron is obtained through heating of filament. Next, we have the anode, which is positively charged. It pulls electrons away from the filament. The condenser of an objective lens has the role of adjusting the electron beam and focusing of image. The scan coils are used to raster the beam on the sample. The 3 common detectors that can be found in SEM are secondary electron detector, the backscattered electron detector, and EDX. And finally, we have the sample stage. SEM is conducted in vacuum environment to prevent scattering of the electrons.
In SEM, the detectors are measuring the kinetic energy of the electrons coming from the sample. When the primary electrons from the source hit the sample, there are various outcomes that can happen. One possible outcome is the emission of Auger electrons. Auger electrons are emitted when an electron from higher energy falls into a vacancy in an inner shell. These electrons are used for material characterization in the Auger electron spectrometry. The secondary electrons are the loosely bonded electrons in the valence bands of the atoms. These secondary electrons are easy to knock off from the primary beam of electrons coming in, and these are one of the electrons that are measured in the SEM microscopy. The backscattered electrons are the primary electrons that return from the sample and back out through the surface. These originate from elastic scattering with the specimen. This image shows where the electrons originate from in the sample. Closest to the sample surface are the Auger electrons. A little bit deeper down come the secondary electrons, and furthest from the sample surface are the backscattered electrons. We'll get into detail now on how this works. In SEM, you normally detect the secondary electrons and the backscattered electrons. The secondary electrons are typically of low energy, normally less than 50 eV. As explained before, these are ejected from the valence conduction band by the inelastic scattering. Typically, the secondary electrons are within few nanometers of the surface, which therefore also provides good information on surface topography. When talking about the yield of secondary electrons within SEM, it is normal to define the secondary electron coefficient. The secondary electron coefficient describes the number of secondary electrons that are generated per incoming primary electron. This number can be larger than 1, as the primary electron continues to go through the substrate and can knock off several secondary electrons at each time. The backscattered electrons are typically of higher energy. These originate from the elastic scattering interaction with the specimen, where the primary electrons will bounce back from the nucleus or the nuclei of the atoms. The variation in kinetic energy coming from the backscattered electrons tells something about the atomic number of the atom that it has been backscattered from. It is also a common practice to establish a backscattering coefficient. The backscattering coefficient tells how many backscattered electrons will appear per primary electron bombarded towards the surface of your specimen. This factor can never be more than 1, as the primary electron is also the backscattered electron, but just with a lower kinetic energy. This figure also shows the energy range for the secondary electrons and the backscattered electrons. For the secondary electrons, they are cut off at 50 eV, while the backscattered electrons can go as high as the input energy from your primary electron beam. It can also be useful to talk about the cross-section. Elastic scattering cross-section refers to the probability for having backscattered electrons. The elastic scattering is, as mentioned, the electron-nucleus interaction, and the probability is defined as per unit centimeter squared. The equation for cross-section can be seen on top of the graph. The cross-section Q is inverse proportional to the incident energy squared, and it's proportional to the atomic number squared. Theta is the scattering angle. We have plotted cross-section against atomic number for incident energies between 5 and 30 keV. As you can see, the trend is that the cross-section is higher for lower incident energy and is also higher for heavier atoms. Again, this means that the probability of backscattering is higher when cross-section is higher. This illustration fits well with the expectations on the basis of the equation as seen above. For inelastic scattering, you can also determine how much energy is lost as the incident electron penetrates the surface. This equation shows the loss in keV per centimeter that it penetrates the surface. As you can see in this case, it's also inverse proportional to the energy and proportional to the atomic number. In this equation, rho is the density and A is the atomic weight of the atom. For high energy incident electrons, the energy loss is lower. This is shown on the illustration to the left. The figure shows a Monte Carlo simulation of the trajectories of the primary electrons. For high kinetic energy, the energy loss is lower and they can go deeper into the sample. The primary electrons that return towards the surface will yield even more secondary electrons before leaving the surface as backscattered electrons. This can be seen on the small illustration on the right.
The final component in SEM is the detector, and we will discuss what detector is used in SEM. The detector used in SEM is called Everhard electron detector. It consists of a scintillator photomultiplier system which amplifies electron signals, improving the signal-to-noise ratio. Detection of electrons with different kinetic energy is possible with this detector by adjusting the bias applied in the detector. The image on the right shows a schematic diagram of the detector and the photomultiplier. Image comparison is done for secondary electron imaging and backscattered electron imaging. The secondary electron image provides only surface topography, while the backscattered one provides contrast, and this is due to the atomic mass differences of atoms detected. Finally, the strength and limitations of SEM. SEM has a wide range of application depending on the detector used. It provides detailed three-dimensional and topographical imaging. Data acquisition for SEM is rapid and is a non-destructive method. SEM is limited by the type of sample it can be used. Only small and solid inorganic samples can be used in SEM. It is an expensive equipment, and finally, analysis has to be done under vacuum environment. So, what is the future of SEM? The graph below is obtained from a market research by Grandview Research that reveals the scanning electron microscope will have continued success. The growth is dominant in the pharmaceutical and semicon industries. According to the report, the key reasons for the success of SEM is that they are widely used by small to medium scale research and development institutes and pharmaceutical companies. They provide the researchers with quality assurance personnel with data regarding surface morphology and properties such as topography, chemical analysis, and spectrography. Increasing demand of nanotechnology-based research and consequent rise in funding is also another reason for the success of SEM. Here are some really cool images taken by SEM. First, going clockwise, first is the image of an ant. Next will be image of cut hair. And finally, we have the image of a ballpoint pen. And finally, these are the references used in our presentation. Thank you.